detailed traces. It does not give rise to a mechanism or a policy that you could go implement. We're going to show optimal results for the full heap GC case and approximately optimal ones for generational GC. The optimization methods are borrowed from machine learning, and I'll mention some tricks we use to make this optimization practical. All right, so program-specific GC. Existing GC performance bounds are framed in terms of the best any GC algorithm could do in the face of any possible program behavior. And this is argued in the usual way for such lower bounds by devising an adversarial program that does the nastiest thing it can in the face of what your algorithm is trying to do. But we're interested in a particular program, or even really a particular program run. So the problem is different. The question is, what is the best we can do in the face of a particular sequence of allocations and object deaths, given a certain amount of heap space? Now, why would this be interesting? Well, in our larger research project, we aim to tune garbage collection to individual programs using machine learning. How would we possibly know how well we're doing? Suppose we indicate X% improvement, say 5% over some existing scheme on some program. Is that good? Is there more to be had? If we fail to see improvement, is that because we haven't done a good job or just because that particular program is very difficult to improve? It's very close to optimal already. So this analysis will help determine whether, and maybe for which programs, such per-program tuning might be interesting. Okay, so let me talk about the model of GC that we used for this. Obviously, we have a heap. We have a program, the evil mutator. So that mutator is always evil in garbage collection work, isn't it? And we have a controller that's going to decide when to collect. So the program can do a couple of things, but the primary one that I'm going to look at first is it can make a heap allocation request. Now this is something where the garbage collection trigger mechanism, the controller, can decide whether to pass that allocation on to the heap, or it can cause a garbage collection. Now, the allocation request size I'm giving here is sigma bytes, and the heap, we can see how much free space there is. So if the allocation will fit in the free space, an allocation action is allowed. Otherwise, if it's not allowed, we must collect, but we can always choose to collect early if that would be advantageous. So right now I'm looking at full heap GC. Now, another thing happens invisible to the controller. The program, either by overriding its local variables or global variables or returning from various stack frames, may drop pointers to objects. It may also mutate pointers in the heap. This results in object death. So we model this by saying, oh, there's going to be some object deaths, certain number of bytes die. And as I say, this is not visible to the controller, and in fact it's implicit in the mutator's actions. We can only actually discover it by running a collector. But for our after-the-fact analysis, it's okay to model it this way. Okay, so let's take a closer look at the heap. It has a free portion, initially the full size S. It has a live portion, initially 0 bytes, and a dead portion. Now, these aren't necessarily segregated into different places in the heap, but we can assign free, live, or dead state, if you will, to any given byte in the heap. And we've got an invariant that these sum to the heap size. So the different actions move bytes from one state to another. So an allocation will move sigma bytes from free to live. So the thing after the colon is the number of bytes moving. So the actions change the state of the bytes, and then a death moves some bytes from live to dead, and a collection moves bytes from dead to free. So it's going to return all of the dead bytes to free, and its cost will be the live size. So we are assuming here for our analysis that the cost is the live size in the heap, something that's more or less true for certain kinds of collectors, popular kinds. Now, of these three, F, L, and D, the only one visible to the controller is F. It can't know what's live or dead. It would actually have to do a collect to figure that out. Right, so the cost model here, as I said, we take the cost of a garbage collection to be proportional to the live size. More or less true for tracing and copying collectors. Since the live size at any given point in a full heap collector is a fixed property of the execution, you've had certain object allocations, certain object deaths up to that point, the cost to collect in this cost model is fixed at any given time t. It'll be different at different times, but at any given point it's fixed. So if we view this decision process as what's known as a Markov decision process, as you've got a state, you take actions, it gives rise to another state, and you have costs. The next state and the cost do not depend on the history of prior decisions. This is what's called a first-order Markov decision process, which implies that it can be solved with dynamic programming. Now, remember, this is in the context of a particular trace. Okay, now, what does that cost us to do when we're doing this offline optimization of, say, a particular trace? Well, if we have n units allocated, initially we'll think in terms of objects, later blocks, the cost to solve dynamic programming problem is order n squared. This is actually reduced to, this is assuming you have the live size information at each point, something that our tracing tool is effectively telling us by telling us the object deaths. Now this can be refined to heap size times the number of allocation units, because you need to look forward or back in the dynamic programming algorithm at most order h allocations. Put another way, your heap collections can't be farther apart than h steps. Right, so what does this give us in terms of GC cost for full heap GC? So we compare against a default collector, which says collect when the heap is full, and see what kind of percent reduction in cost we might get with the optimal computed by this technique. So here I'm showing 7 benchmarks from DaCapo plus javac. And this has been aggregated across multiple inputs and a range of heap sizes. And the box and whisker plot, the extrema give the 0th and 100th percentile. That is the least improvement and the most. The box gives 25th to 75th, and the red line gives the median. And they're ordered in increasing reduction in GC cost, remembering that for us, that's the number of bytes traced or marked. So we see that some programs you can get improvement and some you can't for full heap GC. I'm not going to go into a lot of detail on full heap GC because the generational case is where most collectors are these days, so I'm going to proceed on to that. But there are more full heap GC results in the paper. Okay. Now, there's some things we did to make this optimization more practical. The first was to group allocations into blocks, say 256 kbytes. Previous author used 512. So somewhere around there seems to be a kind of a sweet spot that people use. This reduces the n that I was talking about in the optimization problem by a factor of, say, 5,000 if your average object size was 50 bytes. 5,000 out of an order n squared algorithm, that's a big factor. It does this by constraining where GC can occur. It can only occur on the block boundaries, not between any arbitrary pair of allocations. We found that using smaller blocks doesn't really change things much. Individual cases bounce around some, but the average doesn't move much. Another thing we can do is pre-analyze the object connectivity when objects are dead in the heap. And this allows us to identify objects that will be treated the same by the garbage collector and to summarize the behavior of objects in 3 numbers, as I'll describe in a minute. And it furthermore means we don't have to do any detailed simulation of the heap object graph while we're doing this optimization process. So I think you can see that saves us a lot in optimization and simulation time. Okay, so let's talk about generational collection and how that complicates things. Obviously, the heap is split into young and old portions. Allocation goes to the young generation. Full collection finds the liveness of all objects. Young collection assumes that all the old objects are live, and this means it's going to treat some young objects that are actually dead, it's going to treat them as if they're live because they're pointed to by a dead old object. We call these young objects that are going to get promoted, even though they're dead, baggage. Young collection promotes the apparently live young objects to old space, so both the live and the baggage. So our model with generational GC, we have our three components again. We have heap allocation requests. They can be passed on to the heap, but we have the free space split into two parts. We've got the free in the young space, F super Y, and the free in the old space. We allocate to the young space. We also have available, rather than one collection action, we can do a full collection or we can do a young collection. And then object deaths still happen, but they're a little more complicated. Some objects die in old space, that's the sigma O. Some die becoming truly dead and would be reclaimed in young space, that's sigma Y. And some become baggage, sigma B. So if we look at the heap, breaking it up into the different categories of bytes, we have free, live, and dead in the young space, plus the baggage. And we have free, live, and dead in the old space. So obviously we've got a much more complicated diagram of the possible states of bytes. Allocation moves from free to live in the young space. Death causes three different movements. You have the old objects dying, you have the young objects dying, and the young objects becoming baggage. You've got young collection will reclaim baggage, live and dead objects in the young space. Young space gets completely cleared out, but some things move to old space, the live from the young space and the baggage. Full collection will reclaim the dead space in the old generation. Okay, so much more complicated state diagram, but for those of you aware of GC, everything that's going on here should be obvious and intuitive. Okay. Now, what's the impact on the optimization process, though? Well, full GC and the resulting state after it still depends only on the time of collection. It just has to do with the total live size at that point. This is not true for young GC, however. Previous promotions, the exact history of those, can affect whether a dying object becomes recognizably dead, that is, it'll get reclaimed if we do a young collection, or whether it becomes baggage. And then that affects later costs and so forth. As you promote more baggage, that drags more stuff. It's kind of a snowballing effect. We're going to approximate some of this based on the state that's visible to the controller and limit, rather than giving it the whole history of previous collections, we'll just look at the current time and the time of the previous collection. Okay, how can we compute the overall cost of particular sequence of decisions efficiently? Well, it turns out we can pre-compute the necessary reachability information. I mentioned this before, but now I'm giving you the details so as to avoid heap simulation. So we're given from our tracing tool the birth time and death time of every object. This comes from the Elephant Tracks trace. Elephant Tracks, great tool. Our session chair got it started. I had the fun and good fortune of contributing to it a little bit, but he and his students did the heavy lifting. Now to this, we're going to add something called the pre-birth time of an object. It turns out, and I'll explain how the pre-birth is computed in just a second, but it turns out that if you do a garbage collection, a young collection of an object that's in young space, but at a time after it died, and if the previous collection was between that object's pre-birth and birth time, the object will be promoted. That is, the object is baggage. Now, it might seem remarkable that I could just compute this number and have this work. So I'll show you in just a second how that works, and I hope give you some intuition. We're going to aggregate that according to block boundary and group objects into what in the paper are called cohorts according to pre-birth, birth, and death times. All right, so pre-birth time. Suppose I have some object xn, it has a birth time and a death time, so time is moving here from left to right. And you can take time as bytes allocated or whatever, it just needs to be monotonically increasing here. Now I'm going to consider what's called the dead object graph. So this is the state of objects at the time they die, which other objects they refer to. So kind of imagine a heap where you never garbage collected anything, and there's all these old dead objects there, and the time they die, they're pointing to other objects. So I consider the predecessors of xn in this graph. So the ones that immediately point to it, the ones that point to them, and so forth. And I look back to find, of all those objects, the one that has the earliest birth time. Earliest birth time of any predecessor of x in this dead object graph. Right. So that birth time will be the pre-birth time of xn. And I'm going to argue that a collection between the pre-birth and birth time will promote some one of the xi on a chain from x0 to xn. Maybe more than one, but at least one. Thus, there's a predecessor of xn in old space, and that's going to cause xn to be reachable from old space, and it's going to be promoted. That's the argument. Okay. So to do the optimization process for generational collection, we develop a set of sample states where a state is defined according to the amount of free space in the young and old spaces, the time of the last collection, and the current time. And in each of those states, we determine the cost of legal actions. Can we just do no collection, just allocate, which always has cost 0, but the action might not be possible. Young collect or full collect. Now, to get to that point of having a collection at that particular previous time, t last, we're going to apply a default collect when full policy. Okay. Now, this means we get only a sample. The full search space would be huge. You'd have to generate all possible histories of young and old collections. It's a very large space. So we generate a sample. We hope a useful, substantial sample, but it's just a sample. And we're going to treat this all as a Markov decision process. Even with the process that we were talking about, it's possible to have multiple histories that get you to what's characterized here as a single state. The full heap state would be different and the costs can be different. So you can have multiple samples for the same state. So treating it as a Markov decision process, we're saying as if it were probabilistic and dice were being rolled. What's really happened is we've taken a deterministic thing and taken the states and mapped them down to a projection of their state information. Okay. And then we apply a well-known process from the optimization literature called least squares policy iteration. So you take some starting policy and then you go through, do this development of the cost of the legal actions, and then say, okay, what if I made the best choice at in each state? And then that gives me a new policy. Feed that back around and you iterate, and it's guaranteed to come to a fixed point. Okay. So, as I mentioned before, we did experiments with 7 programs from the DaCapo suite plus javac. For most of these programs, we added more inputs, and there were anywhere from hundreds to tens of thousands of 256 kbyte blocks of allocations. That gives a sense of the size of the optimization problem. Now, each one of these programs we ran under elephant tracks, generating traces of allocation, death, pointer updates. From that, we can compute the pre-birth, birth, and death times, aggregate by blocks, apply the optimization technique, and then we compare with the default collector that just says collect when full. In the generational case, it would say, oh, if the young generation is full, I have to collect it. If the old generation is too full, I have to do a full collection. Okay, so to get a sense of what this does, we've got 2 sample schedules here. So the gray wavy line is the live size curve over time. So time is running left to right, and the live size in megabytes is shown vertically of a run of javac. Now we modified javac. It has various caching mechanisms in it. So we explicitly went in and modified it to turn those off so that after compiling each class, you'll see a drop in the live size. It was a more interesting case to optimize, and it's more like a compiler server. So on the top, we see an optimized schedule. The two blue dots show where full collections occur. The red dots show where young collections occur. So you can see that the blue dots are at fairly low places on the live size curve, and the red dots are mostly at low places. Perhaps a more significant thing is there are only 2 blue dots in the upper one, but in the lower schedule there are 4, as I recall. 4, one very close to the end. And a lot of the red ones are relatively high on the live size curve as well. So the default policy in this case didn't do wonderfully, and you can see what the effect of the optimization process then could be. All right, so here I'm showing a result. This is putting together averaging across all the programs, well, it's by heap size across, and for a particular young generational size of 8 megabytes. What we've done here is plot the mark-cons ratio. So that's the cost divided by the number, and plotted that for the default case of collect when the heap is full, and then the optimized case. So of course the optimized case, if it's truly optimized, it's approximately optimized here. If it were truly optimal, it could never be higher than the default. In this case, it isn't. Cost savings is the vertical difference between these two curves at a given point. It's, I don't know, something like 10, 15%, 20%. But you could also, saving space, you could say, well, for the same cost, if in something like 30 or 40% less, I'm wondering maybe today people care more about that. Broken down by program for the 4 megabyte young generation size, we see the improvement varies between 0 and 20%. With a larger nursery size, the percent improvement is more. Caveat here, with a larger nursery size, the absolute cost of GC drops. So the impact of this on the running time of your program, if GC cost isn't too high, may not be that big. Okay, some additional results in the paper. The improvement really isn't better for smaller blocks. You get more fragmentation. The optimization process empirically measured is about order. There are more graphs and such in the paper. Some ongoing work. Specific policies by machine learning. We collect feature-rich traces, try to train a triggering mechanism. We have some results for what you might call self-tests. That is, same trace, same heap. Generalization over multiple heap sizes, over multiple runs of the same program is proving hard. We're also looking for hard as opposed to approximate lower bounds. And we have results running right now when we get back to some stuff that could appear in a future paper. Baggage, and then solving with dynamic programming again. So it's going to be more like n cubed rather than n squared to solve. So in conclusion, we've offered program GC cost bounds. Policies are promising depending on some programs and heap sizes, giving a time or possibly more substantial reduction or a combination somewhere between the two for a simple default policy. This would be welcome. We're trying to produce those. Our graduate student, Nick Jacek, who's here, I believe, carrying out the reinforcement learning work and the We're developing the traces. Ben, Marlon, and I are co-PIs. I know I was perfectly clear. Right. Looks like Giannis wants to ask something.
Thank you, Eliot. This was great work. Because, as I understand it, the only cost of collection as late as possible is that this may be have lots of live data at that particular point, so the cost of garbage collection is too high at that point.
Yes, it has only to do with the fact that the cost of GC at different times is different. Say a live size curve, intuitively you want to collect it's high. Yeah.
Right. So the problem is just that.
But
you don't of memory. So,
but if you're too eager in collecting when the live size is low, suppose you trained something and it knew very well when the live size was low, but you did that at every minimum, your overall high because you're collecting early.
But why does this give me a higher cost? Okay,
if you keep collecting early over and over, you're going to do more collections, and therefore your overall cost is going to go up.
Okay.
The measure here is the cost across the whole.
The same live stuff again and again. Yeah. So that's understood. But really, your machine rate is that trying to predict the how many. Is the primary thing that you're trying to detect?
Now that's an interesting question. Originally, we framed it that way, and that was the grant was originally funded of just trying to predict the amount of garbage and then put that into a controller. And what we found is that doesn't give you a very strong controller. You need richer information. So our rich feature set will tell you stuff like how many times a particular allocation site was exercised. So you know a lot more about where you are in the. So intuitively, that's why it might do better.
Do you have any insights now how to apply that at runtime? Like do these optimizations at runtime maybe change, invoke garbage collection when it's kind of optimal or close to being optimal?
Well, again, train a collection trigger in the context of a particular program. I don't know to what extent something like V8 could be viewed as a particular program. Is its behavior, can it be captured well enough in one collection of traces for this to help you across the wide variety of things that users might do? But it's certainly more constrained than the arbitrary space of any old Java program.
Well, it depends also on V8 on the mutator, right, on the web page,
right.
What it's doing. I'm just wondering, like, as at runtime, this is really hard, and also the pointer updates, right? Which, like,
an online analysis.
Yeah. Okay. I'm just wondering if the would be it's maybe possible to efficiently compute at runtime too.
Right. I think that if there's some common libraries that impact GC behavior, the context of those might be of some help.
Hey, thank you for your talk. That was fun. In order to estimate the T-last, in order to approximate simulating that using, or you're estimating that, they collect only when full.
We run the system algorithm and say which costs so far. And then more carefully controlling what happens for the next, what we do or what we don't. So you have the T-last and you have
refine that estimate as you're computing your optimal time. I guess I'm just wondering if you did any empirical measurements to see if that was
You can think of it as simulating Heap. Its fully accurate cost But what happens is because you're taking a more complicated state and mapping it down to just a few state variables, you can have multiple samples related to the same state that give different costs.
Okay.
That's the conflation that
I think I
happens.
understand. I'll see you later.
Yeah.
Thank you very much.